Today, I'm Dr. T, and let's talk chemical safety. And to do so, let's think about something that we normally don't consider, but it's absolutely critical, and that is amount, quantity of the chemical. We often talk about chemicals as having certain hazards and dangers, but, well, the amount of chemical matters a lot. See, if you think about a living system, we could be talking a single cell, maybe an ecosystem. In all cases, the living system is able to repair damage. If it's not able to repair damage, it's not going to be a living system for very long. So it's going to be able to repair damage to itself. And also, if it's got some form of hostile chemical, then it's going to be able to either sequester that chemical, neutralize the chemical, or expel the chemical from the system. So a small amount of chemical usually is something a living system can just deal with. But more, well, you can only repair so much, and sequestering, neutralizing, or expelling, you can only sequester, neutralize, or expel so much, so fast. So you're going to run into a problem if there's too much chemical to just deal with. This leads to the famous saying by the 16th century Swedish physician and alchemist Paracelsus, photo over there, "The dose makes the poison." Actually, he said it in Latin. I'm not even going to try the Latin, but it translates to "the dose makes the poison," or "only the dose makes the poison," or something like that. And the idea here is that the amount of chemical is as important or more important than what the actual chemical is. For instance, water can be potentially lethal in excessive quantities. Oxygen as well. Now, when we're thinking about this, we actually want to start thinking not just what chemicals are we dealing with, what hazards are we thinking in terms of the chemicals per se, but also how much of these chemicals we're dealing with. Because those hazards are going to evolve depending on the concentration, the quantity, the length of time we're exposed to the chemical, and how we might be exposed to the chemical. And to do this, I want to introduce this idea known as a dose-response curve. And I'll be putting a few of them over here. These are all going to be graphs. On the y-axis, I'm going to put harm. On the x-axis, I'm going to put the amount of chemical. So we're talking concentration or total dose size, that kind of thing. These are going to be very generic graphs because every chemical is going to have their own specific profile, and of course, things like mode of delivery. If you inhale it versus ingest it versus getting on your skin, those are all going to be very different graphs, even for the same chemical. The first one I'm going to show you is known as a threshold response. I'm only going to do 3 of these, and there's a lot more than just 3. These are kind of the 3 standard, somewhat simplified versions, so I've picked 3 for this curated list. The first one is the threshold model. In this case, you've got a buffer area where at small enough quantities, the biological system, you, are able to just deal with it. Now, I didn't put any numbers on this thing because it depends on the chemical, depends on the mode of delivery, depends if this is a one-time exposure or chronic exposure, etc. Once again, there's a lot of complexities that I'm glossing over here. But the idea here is fairly straightforward. As Paracelsus put it, it's not a poison until you get enough of it. It's not particularly dangerous until you get enough of it. But once you get enough of it, then it starts becoming a threat. And the more you have, the greater the risk you have. So ideally, you want to keep the exposure levels, well, below the threshold. And this is what a lot of government regulations will be. Keep this amount of exposure of this chemical below a certain level. And ideally, that's below the threshold. Sometimes it's not necessarily completely below the threshold. We can always argue about government regulations. That's always a fun pastime. Not. Okay, now some chemicals, living systems really struggle to sequester, neutralize, or expel. Things like heavy metal ions. And so in those cases, while the threshold model definitely makes a lot of sense, and we sometimes still use it, generally a linear no threshold model is a little bit more appropriate. Basically, the threshold is 0. Any exposure is going to cause harm, but the more exposure you have, the more harm you're getting. By the way, these 2 models are linear. Now, it doesn't actually mean that the chemical's hazard is going to be linear all the time. In fact, most of the time it's not going to be linear, but the simplified version of these descriptions of the relationship between amount and hazard would simplify it to linear as a first-order approximation. Depending on what you're dealing with, that may or may not be a line over there. Okay, so those are kind of two. Most of the time you're dealing with some form of threshold. Occasionally you are dealing with those linear no threshold models. Now I will point out there has been some interesting cases where a linear no threshold model was used, at least in a regulatory sense, when really it probably shouldn't have. There's a case from the mid to late 20th century, it's like 1950s, 1960s, where there was a particular tree fertilizer that was contaminating cranberry crops. We had banned it for obvious reasons. You don't want tree fertilizer contaminating your cranberry sauce. The catch was we got really good at detecting said tree fertilizer, and well, we were detecting it at such minuscule amounts that it posed no actual danger, but it did mean that for a year cranberry sauce was banned in the US because just all the cranberries had just a tiny, tiny amount of said tree fertilizer. The history guy has an interesting episode on this one. Okay, so the last model I want to bring up, because not everything is a nice linear more is bad. Some things, more is better until a certain point, and then more is bad. So this is a U-shaped curve. Okay, so on this one, there's a couple of different models. One where you start fairly high up the y-axis at zero concentration. This is for a chemical where there's harm for not being exposed to it. Think something like oxygen. If you don't have oxygen, that can cause a lot of harm. Now, as you increase the exposure to oxygen or you increase the exposure to whatever chemical, the harm goes down and eventually goes into the negative. So negative harm would be benefit. Other versions of this, depending on the chemical, once again, may very well start at the origin. So no benefit, no harm at no concentration, and then you gain a benefit as you increase the concentration. But these curves never go continuously down or flatten off. At a certain point, too much is too much. So they're always going to arc back up. You're always going to be starting to cause harm, and you can overdose on anything. Literally, you can overdose on oxygen. It is possible. Now, for these, obviously your exposure, you want to kind of hit that sweet spot. You're trying to hit the bottom of that curve. Maybe not necessarily the very bottom if you're way too concerned about crossing over into the overdose category, because these are not necessarily symmetrical shapes, so sometimes it could be really interesting shapes there. I hope this has given you a few ideas as to ways of thinking about concentration. When you're dealing with chemical safety and chemical hazards, you need to think about what chemicals you're being exposed to, but also how much of those chemicals you're being exposed to. Are you being exposed to those on a regular basis as a chronic exposure, or is this a one-time thing? Living systems, if they get a little bit of impact, one time, they can repair the damage and then be done. If it's over and over and over again, the amount of damage they can just keep repairing is much less. So a chronic exposure is always going to be much worse than acute exposure to the same thing. So what chemical, how much, and how are you being exposed are definitely things to consider when doing the risk assessments. And in general, just try and keep all those as low as possible. With that said, have a wonderful and safe day.